Welcome to Ghostlike's channel. In this video, we'll go over the folds and reductions. Let's start with the fold function. That one is fairly simple, as all it requires is a stateful loop. It threads the state element through the array, applying the provided function to each of the elements and accumulating the result at the end. There are many kinds of folds that could be done besides the sum, such as min or a max. Since this is a sequential fold, the time it takes to execute it is proportional to the number of items in the array. Let's go over on how it is implemented. In our previous video, we implemented the state threading loop. That function folds over an integer range, and to derive a function that does the same for arrays, all we have to do is pass it a function that uses that index to index into arrays. As it happens, we already have one in the old core library, so let's just bring it in and dust it off a little. Then we will try running it on the test bench. If you remember from the previous video, the number we should get at the end is 15. On the screen, the types of the two fold functions seem to be correct. What we will do next is replace those maps with a fold and print it out. We'll start the program off by initializing an array of 5 elements from 1 to 5. Then we will fold over it, summing the elements as we go along, and then we will pass that result to the console outstream. And everything seems to be in order. We got the 15. Let's move on to the next part, which are reductions. Reductions are more restricted, less general versions of fold functions, but they have better performance properties. As you can see, the reduction operations can be done in parallel, and it would take base 2 log steps in the number of elements of the array to execute a reduction operation in parallel, meaning an array of 10 or 24 elements would take 10 steps. For a fold, since it is sequential, it would take just as much as there are elements in the array. For that reason, reductions are of great interest to a parallel device programmer. In our own work, no doubt we'll be using them to implement various normalization operations, and maybe even the softmax. Well, as far as the common ML operations are concerned, we could expect to find them in a library somewhere. But for those that aren't, a generic reducer will be quite useful to have on hand. Right now, we still haven't looked into Xilinx's ML libraries, nor do we know how compatible the standard C++ libraries are with FPGAs, so we'll make these just in case we need them. The way we will implement reduce is by splitting it into 2 parts. The first one is the step function you see here. It takes in 2 arrays, the input and the output, which has dimension half the size of input rounded up. It is essentially doing the tree reduction you saw on the previous slide. The hard part is not forgetting to do the indexing. And by that we mean doing it properly without going over the array boundaries like we have just now. The second part is the unroll function. Since the array sizes are statically known, we can iteratively unroll it, having the dimension each time. When the output dimension reduces to 1, we just output the result of the reduction operation. When programming in Spiral, you have to keep in mind whether you are working with static variables like literals or runtime variables. If the variables are statically known literals, you can do this kind of recursion very safely, with the expectation that the inlining recursion will not send the compile on an infinite loop. In fact, in contrast to other languages, it is actually very easy to write a program in Spiral that would stack overflow the compiler. You could write something like an recursive loop that doesn't halt, and if you instruct the compiler to inline by not putting in the dines or the let statements, it will try to inline everything until it runs out of memory. But in turn, you get powerful generative capabilities that are far simpler to use than something like C++ templates, and unlike macros, Spiral's partial evaluation works bottom-up rather than top-down. Here you can see the compiled output. Take note of how the loop is unrolled and generated 3 times, first to reduce the array to the size of 3, then in the next loop to a size of 2, and then finally the size of 1, which gets output at the end. There are numerous different ways of doing the reduction operation besides this one, and most of them would produce less C++ code. But the thing about this one is that it is very easy to reason about and implement. The in-place versions used on the GPUs, for example, are harder to grasp than this one. One advantage that this way of implementing reduce has is that it would play well with array partitioning that you can do in the Oculus C++ backend using Pragmas. On the GPU, you'd load the arrays into shared memory, which doesn't have problems with strided accesses. But FPGAs, on the other hand, are more restrictive and need to distribute the accesses across databanks. We won't show how it could be done here, but if you tried doing the in-place version of the reduction, you'll probably run into latency issues on an FPGA. Originally, we planned to show some other reduction operations, but let's cut the video short here. Right now, we are feeling very impatient and insecure. GPUs broke our heart in the past, and so has being stood up by AI chips. We find it difficult to trust another piece of hardware ever again. So now that we've gotten used to programming FPGAs in Spiral just a little, why don't we just dive right into it and start work on the no-limit hold'em game? That will tell us right away whether FPGAs are actually worth paying attention to. There would be no point in doing these trivial tutorials for a month only to realize that FPGAs have crippling flaws, preventing them from being useful. In the next video, we'll start things off with the hand-ranking function and see whether it synthesizes to hardware. Hope you've enjoyed this one, like and subscribe, and see you in the next one.